Hello, and welcome to today's lesson in BCIT Technology Teacher Education 4044. This is our structures class, and we're going to be doing some fancy stuff and getting some pretty pictures today as we take a look at a way to do virtual analysis of our truss designs for our truss design challenge. With this being 2021, we're not going to get as much time in the lab to cut things out on the laser and do iterative trials to get the best possible truss. So we're going to have to figure out how we can use the computer to get some virtual results and optimize our design cycle times. Interestingly, this is how a lot of industry is shifting. And over the course of your teaching careers, I expect you are going to see amazing advances in computer interactivity. I don't know if you've tried the Microsoft HoloLens yet. Little glasses that fit on over your eyeballs there, like a big heavy sunglass, and you can actually see the truss sitting in front of you in 3D as a hologram. It's really cool. It's really amazing. The technology is advancing out there, and it's going to keep getting better and better. And I wouldn't be surprised if one day you're actually sitting there. Maybe you have gloves on, or I don't know, nail polish or something, so that makes it easy to identify where your fingertips are. And the camera up here will tell how your hand is interacting with the structure, and you're modeling and putting things together. Then you go and create it, and it behaves just like you predicted it to. But we're not there yet. There's still lots of room for the mouse, and I'll mention my special favorite tool, the 3D Connection 3D mouse. When you start getting into your 3D modeling, the 3D mouse is a really neat interface to the outside world, but you don't need one. It just makes you happy when you've got one. So let's get started and take a look at what we're going to be doing today. I've got a whole bunch of windows open on the screen, and let's grab this one first. Now, I've handed this document out to you already. And so this is our Laser Truss Challenge, the 2021 revision. It's got all the rules for our truss design challenge. And I'll just go over a couple of them before we start doing too much design here, because there's a diagram right here that shows you the mandatory dimensions. So you're going to have a pin, actually this will be a pin support, not the roller support here. You'll have a pin support at this node, and then you'll have your load at this node. They will be 400 millimeters apart. Then you'll have another support down here, 150 millimeters apart. Now you can make this as tall as you want, but this box represents the 18 by 24 bed of the laser, and you have to be able to fit both halves of your truss, because you're going to have two parallel, pieces of truss joined together with dowels. You've got to fit them both into one piece. So you can't make it too tall. Otherwise, when you flip this around to cut the other half, it's not going to fit. Okay, so do go through and take a look at the rules, because it's got rules on the dimensions that you can have for the nodes on your truss. And you've got to have your nodes at least 70 millimeters apart. So you can check that in AutoCAD just by drawing a circle around the node. And so long as it doesn't overlap with the center of another node, okay? It's a center to center distance, not an edge to edge distance. So long as the centers of your nodes are 70 millimeters apart, you should be good with your design. Okay, so there is a file up on Desire to Learn for the BCIT students that looks just like this. It's got these nodes in here, and it's all set up and ready for you to start. And from there, you can go in and you can start designing your truss. Sounds simple, right? Well, where do I begin? Okay, well, you begin by reading the rules and go through and double check and make sure you understand all the rules. And when we're done at the end of the day, we're going to have a pretty picture that looks something like this. And we're going to be able to come in here and take a look at our truss and say, well, where is it likely to break? Where do we have to go back to strengthen things? We'll come back to that later. And to get there, we're going to travel through AutoCAD. And you just pop that up onto the screen right there. And I started designing a truss right in here. And this is the one that I'm going to analyze for you as an example. Just looking at it, I've got a feeling that it's not that good. And I'll do a couple of calculations on here and show you where I think it might fail. But I do want to go over a couple of things about doing this truss design. So the red nodes right here were included with the file, and those have the required 400 millimeter and 150 millimeter spacing here. And this box that you're looking at right around here has the 18 by 24 dimensions of the laser bed. I think that's 600 by uh, something in millimeters. And so before you go and get too excited about your truss, I do suggest that you make sure that you group it and copy it and rotate it and make sure that you can fit 2 copies of it into that one piece. So I came along and I said, well, if I've got to fit 2 copies in, this looks about as high as I can go. And that turned out to be 225 millimeters. In the end, after I flipped around, I might be able to go a little bit higher, but I was thinking I wanted to go high in here because, as you know, when you have a vertical force, the higher the edge of the triangle that you can make it acting in, the lower your horizontal forces are going to be, because of course you've got the components to your vectors, the x and y components, and it's a triangle thing. So the higher I could make this, the less horizontal force I'd have to deal with in the bottom or along these edges. It may or may not have been a good design decision because, of course, going higher makes the truss heavier, and we're limited to 75 grams. I'll talk about how you can estimate the mass of the truss in just a moment. So anyways, I started out with this, and I took a look at it and did a few little calculations, and I'm just going to bring this window up to a larger size so we can just quickly go over some of these calculations and what I was looking at to make this all come together right here. So here's just some hand calculations that I'm doing, and I think it's really important that you know the hand calculations and that you understand the hand calculations before you start doing your computer analysis. Okay, computers can provide insight, but rarely do they provide solutions. In fact, given the luck that I've been having with them this morning, they've provided more hassle than solutions. So anyway, let's take a quick look right here, and we know some things about this truss. It's required to be 400 millimeters from the from this node to the force, required to be 150 millimeters right here. And as I was just saying, in my design, it looked like I could get about 225 millimeters tall and still be able to flip the truss over and make a second copy of it up there. Could probably go a little bit taller than that. I'm not 100% convinced that I should, and even shorter than this might be better. I really don't know right now what the optimal truss design is going to be. However, I do know that I can do a few calculations on here to help me figure out what's going on at the truss. Now, I don't know what my force is going to be. Trying to I'm trying to make this as strong as I can. I'm just going to call this F for now, and I'm just going to leave that as a variable, but I can come up with some ratios. And so just by balancing the moments about this point right here, I've got F at 400 millimeters and the reaction force acting up right over here, okay, is going to work out to be F times 400 divided by 550, or that should be about 0.73 of F, pushing right up there. So if F was 10 newtons, I'd have 7.3 newtons. If we managed to get 100 newtons onto F, that would be 10 times as much. Okay, and if I've got 0.73 newtons pushing up right here, then down over on this side, my reaction force down here, because of course this side and this side have to equal to F, otherwise we're accelerating up or down. This one is going to be 0.27 F right in there. So I certainly expect you to be pretty comfortable doing that type of calculation. Now, the next thing I'm going to take a look at is what are my forces going to be along this side here and this side right here if I was just to design it as a simple single triangle. Okay, again, I'm just trying to get an understanding of the forces so that I've got an idea of how much something is in tension, how much something is in compression, and it's a really good starting point. It is something that I expect you to be able to do. Now, one of the nice things about drawing this in AutoCAD is if you want, you could just use the dimension function to measure right in there. Of course, Pythagoras still works, 400 squared plus 225 squared. Take the square root of that, and you should get something around 459 millimeters long. So that's going to be a fairly lengthy member right in here. And over on this side, we should get something about 270 millimeters long. Okay, so now that I've got some dimensions on the truss right here, if I've got 0.73 of that force pushing up right here, okay, then that means I've got 0.73 acting in the 225 dimension coming right up here, okay, so that's my Fy. So I want to figure out my force in that actual member, and that's going to be 0.73 of F, or just go 0.73 0.73. This is my reverse Polish notation calculator. So I'll divide that by 225 and multiply by 270. And so the force acting right along here should be somewhere around 0.88 F. Okay, and then my force acting over on this side can do the same sort of thing. I've got 0.27 of F pushing up this way, so 0.27 of F, and divide that by 225, multiply by 459, and I should have 0.55 of F acting along that way. And to calculate the force in the bottom, now keep in mind, these forces are both going to be in compression, okay, if we've got a node coming up and down right here. We can't really just have one node right here without a member coming up and down in the middle right here, okay, and that node is perfectly vertical, and it's going to have F acting in it, and that F is going to be acting in tension. Okay, so we do need a member coming up and down right here because this node can't support any vertical force without it. We need something lifting up on that node. This line is perfectly horizontal. This line is perfectly horizontal. They cannot provide the vertical support we need on here to resist any kind of substantial F down there. So it'd be very weak to build this without something. It could be coming up at an angle in here, okay? But you need something holding this node up. These two right here are just holding these bottoms from popping out like that. Okay, and we can calculate the amount of tension force in the bottom right there by saying, well, over on this side, if I've got 0.27 F acting upwards right there, then 0.27, and that's acting in the 225 dimension, and then that's 400 long, and that gives me 0.48 of F in tension right here, in tension right this way, and you can do the same calculation over here, and this one also better be 0.48 F. Now, these are simple hand calculations, but they're important to do, and it's important to think about this before you send the problem over to the computer, because it's entirely possible to put the wrong numbers into the computer or to put something into the computer that doesn't make sense. And if you don't have a prediction or an understanding of the data that you should be getting back from the computer, you're not going to be able to catch the mistake. The computer can pull a fast one on you if you're not careful. So think this through. Now, what this tells me right here is that this member right here is going to be my highest compressive force. Okay. However, this one over here is going to be my longest member right in here. As you know from our compressive tests, the strength of a member is inversely proportional to its length squared. So in other words, if these were the exact same members right on here, this would be a considerably weaker member, okay? If because it is 4.59, 459. This one's 1.7 times as long, okay, which means that this one is 1.7 squared, or 2.89 times as strong in compression at resisting buckling as this one is over here. So even this one, though this one's carrying more force, um, it's it's shorter. So if I just leave it like this this member over here is likely to buckle first. So I'm going to break these down into smaller sections, and I'm going to put a couple of nodes in right here. I'm going to break this one down into some sections right here, break this one down right here, and now I need to brace those nodes. And so to do that, I've added a couple more nodes right in here. And so I've come up with a design. I said, well, if I've got that there, maybe I'll bring this one down. And I just arbitrarily offset this, brought it down in here, and came up with a structure that looks something like this. Now, I didn't think that was a brilliant structure. I don't think this is going to be my final solution, but I figured it was a good starting point to go in and analyze some of the forces in the truss. Now, one of the things that I did do here, because I broke this side down into 4 sections right here, now each of these chunks is going to be 459 divided by 4. Each of these chunks is going to be 114 millimeters long. Okay, and whether they should be evenly spaced or not is something I'm going to ask the computer to give me an idea. And over here, it's going to be 270 divided by 2, which is going to be 135 long for that member right there. Now, again, this doesn't look really good because I've got higher force running down right here than I do over here. And now these are shorter. So these are the stronger ones now, but dealing with less force, whereas this is a little bit longer. So by taking a look at that, I'm going to make a prediction that if I have a buckling failure, it's probably going to come over here somewhere because I've got a longer member subjected to more force, and maybe I should have put 2 nodes in there. Maybe I only needed to put 2 nodes on this side right here because it's not seeing as much force. It's important to go through and sketch things out and get a sense for what's going to happen, because when we go and do the results, yes, they'll probably be accurate. But if they're not, you need to be able to catch it, because the computer's not going to come along and say, you gave me bad data, I gave you a bad answer. It's just going to give you the bad answer. So let's take a look at how we go about getting that answer, good or bad, and then confirming it one way or the other. Okay, let's take this window right here, and no, let's hide it for now. Okay, so here's our AutoCAD drawing, and let's just zoom in on here for a moment. Okay, so it's built into this box. And we've done a simpler design like this just so that you had a chance to get the hang of coming in and drawing all this. And just to remind you, I didn't start off drawing all this. What I started off was drawing a line from the center of one node to the center of another node. Okay, so I drew a line right in there. And then I came in and I did some offsets, and I used the offset command to make it go out to that side right there. And then I came into the end and I used the trim command and the erase and then the fillet command to smooth things out right in there. And the net result is that I come up with this structure that looks something like this. Now, in a previous lab, I asked you to measure the mass of a chunk of MDF and also to measure its size. And if you went and you did that, our 18 by 24 sheets of MDF, I forget exactly what they weigh, but we came out with a mass for the MDF of, just taking a look at this, the density came out to 0.9, which makes sense and matches all the predicted properties for MDF. So 0.9 grams per cubic centimeter, or a specific gravity of 0.9. In other words, it's slightly less than water, so it'll float, but it's about 50% heavier than some lighter woods that come in around a density of 0.6. And if you've ever carried a sheet of hardboard or a thick sheet of MDF, you know what I'm talking about. Whoever called that stuff medium density fiberboard. Well, the MDF has got a density of 0.8, so I guess in comparison to hardboard, which we're dealing with, it is a little bit less dense. Anyway, when you do that and it all works out, it gives you a mass of 0.0027 grams per square millimeter, because we're working with a 3mm stuff, so we only need to know the area. We already know how thick it is. We don't have to work that into our equations. So 0.0027 grams. So we can use this drawing to calculate how much area we have right in here. And to do that, what we're going to do is we're going to use the hatch command, I believe. And now when you do this, your screen might get a little bit lunky and you have to move the mouse carefully and just pick a point on the inside of the object that you're trying to work with. And you should see a hatch pattern suddenly appear right on there. Don't worry, we're going to get rid of it. We don't want to cut all those lines. But what that's done is that's identified, it's gone through, it's picked out the entire area, the area enclosed by the lines that you've drawn. And importantly, it's also showing you that you've done a nice job of trimming all those ends. And if you get a good hatch pattern, you're probably going to have good results when you move this over to Fusion 360. Now, if you come in here and just hit enter so the hatch is done. There we go. If you come in here and highlight your hatch, there you go, get the hatch nice and glowing right in there, and then right click on it and go properties. All the properties of the hatch will come up, including the area right down here. Now for my truss, the area came out to 12,118.961. You don't need to worry about all the decimal places. These are square millimeters that we're talking about. Came out to 12,118 square millimeters. And we know from our calculations that a square millimeter of 3mm thick hardboard that we're working with should weigh 0.0027 grams. So if I take the area and multiply by 0.0027 grams per square millimeter, this tells me that my truss right here, this piece of MDF, is going to weigh 32.7 grams, which doesn't sound too bad because when I go into when I go make it a two-sided truss, that's going to take me up 64 or 65 grams, and that might leave a bit of mass left over for the wood joiners and the glue that's going to hold it all together. Will that be enough? I don't know just yet. That'll take a little bit of experimentation and calculation, and Fusion 360 will actually help us out a little bit with that. Okay, so once you've got that area and used it for your mass calculation, you can close the hatch properties and undo that. You don't want to keep that hatch on there. Okay, so we've got a truss designed in here and we're interested in seeing how this is going to behave. We've made some predictions and we've said that these members right here have the higher compressive stress in them. They're a little bit longer. I don't quite know how all of this is going to behave right in here. I can see this force coming down right in here is messing around a little bit with what's going on down in the bottom. And this design would actually be really, really complex to try to calculate by hand. It can be done. I mean, obviously, people built trusses long before computers came along. But if you've got Fusion 360 installed on your computer, then I think you're going to be happier to solve it using Fusion 360. So let's get this file out of AutoCAD and in a format that we can take it into Fusion 360. And I'll show you how you can go about fairly quickly and easily doing a calculation that I'm pretty sure would have earned you at least a master's degree when I was a BCIT student. Okay, let's take a look right in here. And what we're going to do is we want to go save as. Now, of course, make sure you've saved it as a DWG file. DWG is AutoCAD's generic file format, or its native file format, but DXF is its transfer file format. It's a simplified way to store your AutoCAD files. AutoCAD published that, so like I don't know how many decades ago, AutoCAD published the DXF standard so that other manufacturers of or of CNC software, of graphics software, of any kind of software out there could communicate with AutoCAD. And DXF has become a pretty cool standard right on here. So come to your drop-down menu and you'll see it's got all the DWG formats, which are kind of proprietary to AutoCAD. Other people have figured them out since. But then you've got the DXF format that's really intended for transferring files from AutoCAD to other pieces of software. So I'm not too worried about what year I use because I'm working entirely in Autodesk products. If you're using an older piece of software, you may have to use an older DXF format to work with it. And I'm just going to save this as TTED4044 Truss Analysis Demo 2021. And since I'm doing this, I'm just going to call that live because this is my live demo. I've already gone through and practiced this once or twice, so fingers crossed it's all going to work out okay. All right, so now we've got this file saved in a format that we can import to Fusion 360 and start Fusion 360 up. And you're not going to be looking at anything quite this beautiful on Fusion 360 when you log in. In fact, you're going to be mostly looking at a blank screen. Let me just maximize my screen real estate here. Now, on your screen, you may be seeing right in here, where does it, there's usually a little window that pops up in here showing us what file is in which. Anyway, I hit the close button and it's gone, and there is a way to get it back. Oh, right there. There's your dashboard right in there, and you can just close that to get rid of it. You can see I've analyzed quite a few trusses in here, and I've done this one once before, and I'm just going to close this for now. And this is more what you're going to be seeing. Okay, you're going to have an untitled drawing in here. You're going to have some icons along the top. And over in this section, you're going to have what we call the view cube. Now, if you haven't had a chance to play around with Fusion 360 yet, you do need to have a way to rotate things around in space. And like I say, if you're going to be doing a lot of CAD work, 3D mouse. Just take a look at that. This is by a company called 3D Connection. And I will happily sing their praises. Very nice toys for working with CAD for, less than 200 bucks, let's say. A little expensive when you're a student, I know. But hang on to there, and maybe some of your Pro D money when you're teaching or something like that could come in really handy for getting a 3D mouse. Something to look forward to. Alrighty, so what we're going to do is we're going to start by importing that drawing that we just exported. Okay, so we took it out of AutoCAD as a DXF file. Now we want to bring it in here. Now, Fusion 360 works in 3D space. So what we do is instead of using that as a drawing, we use it as a sketch. Okay, and we're just going to put that sketch on a planar face. We've got 3 different planes that we can put it on. If you click on the wrong plane, don't worry, everything will make sense in the end. I'm just going to put it on this plane right here. And as you can see, I chose the ZX plane. And right up in here, we've got our different axes and our view cube. And to put our sketch in there, I'm just going to come in here and go Insert, and I am going to insert a Dxf file. And it's going to ask me what file do I want, and I am going to bring it in from right here. So I click on the little folder icon, and this comes up. And I'm going to have to navigate through my folders up at the top. And I know mine's in the Math Science Structures folders, but you're going to have to figure out where you saved yours to. And as you can see, I've been doing different Dxf files and trying different things out. And I called this one Truss Analysis Demo 2021 Live, just because I started out right here. And when you do this, you should see something like this coming in here. Okay, now it's upside down, whatever. We'll flip it around and we'll make the entire world work. Let's just click on OK from our Insert DXF, and now we can take a look at it right here. And what's critical is that if you zoom in a little bit with your center mouse button and put your mouse over top of some of these sections, you see how they go dark. You want to be able to come in here, put your mouse over top of one of your nodes, and see your entire truss go dark like that. Okay, because if your truss goes dark like that, that means that's one enclosed space. If your hatch command worked, then this is probably working. If you didn't delete the hatch afterwards and you just went and exported it, you might be having some problems right there, but that's a good sign if you can do that. Okay, now before we go on too much, there's a whole bunch of extraneous lines, and let's get rid of them before we go too far. So just come in here, and by pressing the delete key, you can come in and you can start erasing the lines. We don't really need the rest of these lines in here. They probably won't cause that big of a problem, but let's get rid of them just because we don't need them. Okay, so now what we've got is we've got our truss right in here, and that looks good. It's just the truss, and we're going to finish our sketch. And that drawing pops out right here. And yeah, it's still upside down, but don't worry about it. Maybe yours is upside right. If you're worried, okay, if you're worried, you can come in here and the view cube lets you flip around from view to view and rotate around and look at things from different angles. Okay, you can grab the view cube and drag it up to whatever angle you want. So click and hold on the view cube, or come down here and you've got the orbit button at the bottom of the screen that lets you rotate this around. If you click on the inside of that little circle right in here, you see there's a circle running right around here. If you click on the inside, then you rotate around like that. If you click on the outside, then you rotate slightly differently. Okay, I'm just going to use my mouse because I'm so used to doing it. I'll flip it up into space like that. Perfect. Okay, and just hit escape to get out of that orbit mode. Okay, now what we're going to do is we're going to do an extrude, because right now this is just a sketch. It's flat like a sheet of paper, and we want to make it 3 millimeters thick like our truss is going to be. So you click on extrude, and you have to give it a profile plane. And this is why it was so important that we had that nice, that drawing go gray for us. Click on that right there, and it wants to know how far do you want to extrude it. So right down in here in this box, you can tell it you want to extrude it 3 millimeters because your truss is going to be 3 millimeters. And now you can take a look at that, and it's looking pretty darn good, I'd say. Okay, we've got a member of a truss in here. Now we're going to apply a material to it, and we're not going to apply the perfect hardboard material because it distracts a little bit from the presentation when I explain how to get the perfect material. We're going to use MDF, which isn't quite as stiff, isn't quite as dense, but we'll take a look at that. What we'll do in here is under your bodies, click on the down arrow. There's body 1. If you right click on that and tell it that you want to assign it a physical material, okay, then you'll have a window pop up over here, and it will give you a choice of different materials. And if you look in the wood materials, you'll find medium density fiberboard. And you can just drag that right onto the material. And when you click it on there, you should see a slight change in the coloration because now this is designed to look like MDF. Now what's really cool about that is you can also come in here and you can check the properties, okay? And when you check the properties, it tells you the mass is 29 grams per cubic centimeter, which you can see it's only using a density of 8 instead of a density of 9. And again, you can change and edit the materials. That's just going to distract from things if we spend too much time doing it. But if you take the volume that we've got right here and multiply by 9, you've got the correct mass for that truss, which is around 32 grams, which we already calculated using the AutoCAD information. So this is good. We're checking our data as we go along, and things should be making sense. Now, we've got one half of our truss in here, which is really nice. Hopefully that was fairly easy for you to get in there. What we're going to do is we're going to make the other half of the truss using the move copy command. So we've got this selected right in here. Okay, if you don't have it selected, that's okay. Click on move copy, and the first thing it'll do is it'll say select. Okay, and just try to select something where you've got one of your axes pointing perpendicular to that plane. It shouldn't be too hard to do. Okay, you see I've got two axes that rotate depending where I click on the circle, and I'm not worried about which side I'm clicking on right here. Okay, now before you move it, click on the Create Copy button right there, because if I click Create Copy, I drag it over, and I'm just going to do 50 millimeters. You could do wider, and that would let you know whether or not a wider truss was going to be more resistant to buckling. You could do narrow. You're allowed to go right down to 18 millimeters wide. So you could take it down, and that's going to reduce the weight of all the dowels that you have coming across right in there. So you can try lots of things. I'm going with 50 just because we tried that in a lab previously, and it seemed you got to start somewhere. All right, so now we've got these two sides, and we need to join them together with pieces of wood. Now, in the real design, you're not going to put wood in right here or right here. That's where we're going to slide a steel rod through to hold everything onto the testing jig. And in fact, you don't even have to put wood right through here. You are allowed to put wood right through there. We'll put a hook over it, but if you don't want the weight of that coming through in your structure, we can just put a bolt through there and use the bolt to apply the weight. The bolt adds a little bit of force to the load, probably marginal compared to the overall mass of what you guys are going to be dealing with. Alrighty, so what we want to do is we want to join them all together, and for the purpose of our simulation, so that we can apply supports and we can apply the load, we are going to put material across in each one of these, but it's not necessarily the case that that's what we're going to do for real. All of these ones up here, all the little nodes, all the nodes that you designed, you chose to have them, you've got to join them from side to side. You can't ignore them. Now, you can go down, like we've got 1/4 inch dowel, that totally counts. You can use a barbecue skewer to join them. Okay, you can go very small in what you put across there. I think there might be some benefit in using a 1/4 inch dowel or even a 5/16 dowel going across in there. That usually works out if you're cutting the holes to about 6 millimeters or 8 millimeters in diameter. Remember, when you're doing your design, to cut your holes with diameter, not radius. And anyway, how do we get those pieces of wood going across there? Well, we're going to create another sketch. So right up here, same command, create sketch. But this time, instead of clicking on one of these three planes down here, we're actually going to click on the planar face of one of the two trusses. Now, choose an outside face. Don't choose the inside face, okay? Choose an outside face because we want our members to go from the outside to the outside so that they're actually joined together right in there. And now we're back in this upside down mode. How nice. And so what we're going to do is we're going to hit the P command. And the P command brings up this project window, and just put your mouse over top of that profile, and that takes all the information from that extruded shape and just translates it, projects it right onto that plane. And there's a lot more powerful things you can do with the project command, But what that did was it just gave us all the information we needed for creating the wood, and we can click OK, and we can finish our sketch. So P, project, very powerful command. Now what we're going to do is we're going to do another extrude. Okay, this one's going to be a little bit different because we're going to extrude multiple surfaces. Now don't click on this big shape. You got to watch for that. You just want to click on those little circles. See how they turn blue after you've clicked on them? And a little arrow pops out from them? That's what we're looking for right there. Don't click on these ones on the backside by mistake, okay? We're just working on this surface right in here. And I'm just using the center mouse button. If I click on it and drag it, then I'm able to pan. And if I roll it, I'm able to zoom. Let's see. And I like to zoom in on them to make sure that I'm clicking accurately. And then I like to zoom out to make sure I've got every node showing up. You can see the little red circle around there. It's blue on the inside, and I've got all of my nodes selected. Okay, nothing else selected, just those nodes. And so what I'm going to do is now I am going to tell it, I'm not going to extrude at a distance this time. I'm going to tell it I want to extrude to an object. And then I'm going to use my orbit command down here. Going to click on the inside of that little circle, rotate it around so I can see the other outside face right in here. Hit escape to get out of orbit mode. And then click on this outside face right here. And now what it's done is it said, well, I'm working starting in this plane right here, and it's extruded right through to this plane right here. And you can see we've got the join mode turned on. So basically, we've told it that we have a continuous body of MDF right here. Now, it's not quite true. Of course, these are going to be steel rods. These are going to be dowel that you've got going across in here. But just click on OK, because that's probably good enough to get started. Now, you can use the view cube to get back to a nice view for looking at this. And in a matter of seconds, okay, especially if you're not yapping as you go along and do it, and you've done this a couple of times, you can create a pretty nice 3D model of what your truss is going to look like. And the cool thing is, because you applied a material to it, it is now ready for testing. Now, if you really want to be accurate in your testing, okay, you can look up how to create a Fusion 360 material and give it a unique color if you want, so you know you're using the right material. And we know that our density for MDF is 0.9 grams per cubic centimeter. And I also can tell you that the elastic modulus is 3.5 gigapascals. I went in, or 3.5 GPa. I went into the shop and I did some testing on there. I've got a little video of how I tested that I can share with you later. Okay, so we've got this all ready to go. Now save this file. Okay, it'll ask you where do you want to save it. Fusion 360 saves everything onto the cloud, so it will store it with your Autodesk account on the cloud. You can log into Fusion 360 from any computer that has Fusion 360 on it, and you should have access to your files. Okay, I'm just going to save this as test truss number 1. Now, the other neat thing that Fusion 360 does while it saves everything to the cloud is it gives them a version number. So you can see right there, I was at V0, I just saved it. Now I'm up to version 1. And the cool thing is that if you make a mistake in your design or you do something that you don't like, you can go back to a previous version of the files that you've saved. So let's see right now, we're ready to do some analysis. So from the design mode up in the top corner, come down to the simulation mode right here. And the first simulation that we're going to do is one called structural buckling. And this is actually what led me to using Fusion 360 in the first place, is there's very few software packages out there that do the structural buckling analysis. As you can see, there's lots of other analysis that you can do in here. And the shape optimization one is actually kind of neat, because if you go and read up on that one, it might actually tell you the best way to design this truss. I haven't used it yet, so I can't do a video on it. All right, we're going to create a study right here. And now we're upside down again. Let's we can flip it around right here in the view cube. Oh, I'm trying to use the view cube because I know you don't have a 3D mouse, but yeah, get it close and then use the orbit command to get it lined up on there. Hit escape to get out of the orbit, and then your center mouse button to bring it up right there. Okay, so here we've got a 3D structure. And basically setting it up to do the test is the exact same thing that we did with our 2D truss drawings on paper. We've got constraints. You can do a whole bunch more complex things, but we're just going to put some constraints on here. Start with a structural constraint, and we are going to start with a pinned constraint. And you'll notice that I've said that it's going to be fixed in the radial. So if this is my pin right, there's something a little bit bigger to demonstrate a pin. Here we go. If this is my pin coming right through, when I say it's fixed in the radial constraints, that means it can't move in the x-axis, it can't move in the y-axis. It is, however, free to rotate. Okay, that's the tangential axis, and you'll notice that I've got the tangential not blue. You may have to click on that. It may come in with all of them blue. Turn off the tangential. The axial means that it's fixed this way, so it can't slide back and forth on it side to side. So basically we've got that pinned in place. Okay, and it says what surface are we going to apply it to? Bring it down here and click on this piece of dowel right here. Again, in the real test, this is going to be a piece of steel that we slide right through there. But now, once you've done that, you should see a little pinned joint come in right there. And if you've set it to be, radial and axial, but not tangential, then you're good to go. Okay. Now you're also going to put a constraint. This is going to be a structural constraint, and we're going to put it on this end right here. But notice I'm not using a pinned joint, because this one, in order to properly simulate the fact that the one end of this truss is going to be on a roller, okay, we need to tell it that it's free to slide in one of the directions. And if we look at our view cube right up here, I can see the x-axis is the one that slides along right here. So this is our x-axis. This piece right here is going to be free to slide in the x-axis when I put a load right here, and it's going to be up to these members right in here to stop it from sliding. So I unclick the x. It's going to be fixed in the z-axis. It can't go up and down. Wouldn't be much of a truss if it could go up and down there. And I've told it to hold fixed in the y-axis as well. It could actually slide a little bit in the y-axis, and you can try the y-axis being on or off and see how that affects your study. But pick this surface right here, because that is your other structural constraint that your truss is going to be working with. So now we have two constraints. We need one load, and we're going to put a structural load on here, and we're going to put it right onto the center one. Now you'll see it was clever enough to just guess that we want that arrow going straight down. It might not have guessed that way for you. Don't worry about it. What we're going to do is we're going to set it right here. Look at that, three-dimensional vectors. We've talked about two. And in my drawing, the Z is going straight down. Maybe you chose a different plane at the beginning, and maybe you're getting an X or a Y on here, but I want it to be going straight down in the Z. So I put 1 on there, and it looks like it's pushing straight down on there. So I've got fixed, fixed, and load. And the load looks like it's going in the right direction. I click OK. And believe it or not, That's all there is to it. Now, you're probably sitting there, and if this is the first time you've ever done finite element analysis, you're sitting there saying, well, why should it be any more complex than that? There is so much going on in the background with the computer making intelligent decisions for you. It's breaking this entire structure down into tiny little mesh nodes and choosing the right type of mesh node to use. And anyway, this used to be hard. I'm just amazed how straightforward it is right now. But like I say, it can still feed you bad results if you don't know what you're doing in here. We are going to go and solve it. Now you can do a pre-check if you want, and hopefully it tells you that it has everything required. It's got a material, it's got a couple of structural constraints, it's got a force. If you're not getting an okay pre-check, then you've probably missed something along the way. Let's come to solve right now. And the structural buckling needs to be done on the cloud. Okay, so you can see it says it's ready to go right here. The cloud is the default, and what that means is that Autodesk's going to let you as a student have free access to their servers. Okay, if you are paying for this, if you are a commercial client, I think they charge you about 15 cloud credits, which is roughly the equivalent of $15 US, depending on how many cloud credits you purchase. Select the study you want to solve if it wasn't already selected. And when that box is blue and it says solve one study, solve the study. You'll get a box like this that pops up and it will start doing some calculation. So you've just uploaded your file on Autodesk servers. They have probably 50 or 100 computers, each using a section of their CPU, crunching away to solve this. And they're going to send the results back to you in just a minute or two. I'm going to press pause. When I come back, we'll have some results. There we go. That didn't take too long at all. Came back and we have some results of our structural buckling survey right here. And the first result, as you can see, doesn't make sense. Now, if you're not sure why it doesn't make sense, take a look at this. Think about what we calculated at the beginning and where the tensile members would be, where the compressive members would be, and say, does it make sense that a tensile member would buckle? It's the beauty of tensile members. They don't buckle, okay? Yet it's showing us this right here. However, what you'll notice is it says buckling mode 1 is at negative 13 times the load. Okay, down in this little box right in the corner right here. And this is something that drives me a little bit nuts about this solver, is it's a well-intentioned feature to alert design engineers that if the load is not going in the direction that they expected, that there might be a weakness in their structure, because sometimes you do have designs that get loaded backwards or different from what the engineer designs. Instead of putting something under pressure, it gets put under compression and it all collapses. And so this is predicting. We said we were going to put a 1 Newton load right here at 13 times that. So if we had 13 Newtons pressing upwards in here, it's predicting that the structure would fold in like that, causing buckling right here. We want to know what is the lowest force that's going, lowest positive force that's going to cause it to fail, because we're not worried about the negative direction. So we have to come over here and there's a whole bunch of different results, and I gotta say, none of them. That one's actually rather pretty. It's still wrong. None of those results actually tell us how that's going to fail if this is under a positive force coming down. To get that positive response, what we need to do is we need to come in here, and when we set up our study, okay, we need to come in here and right click on there. We need to tell it in our settings, okay, we need to get it to give us maybe 80 modes. Depending on your design, you might need more than 80 modes of failure. In our case, I've done this once before, and I think somewhere in the first 80 modes of failure, we do find a positive failure mode. So once you go and you change that setting, so again, that was right click on study one, settings, and number of modes, just change that up to 80, okay? Click OK. And now you have to go back and solve it again. So let's finish our results. We're done looking at the pretty pictures and come into solve. And there you go. Yeah, 15 cloud credits. Thank you very much, Autodesk. And here we go. Solve that one study. It goes back and it solves it all over again, just like it did before. So I will just press pause here and rejoin you. And this time we might have some actual. There we go. The results are back. Again, it doesn't take long. It takes about the length of time to go pour yourself a cup of tea or something like that. And here we go. We can see that buckling mode number one is still a negative failure. So you got to click on this chart, click and hold on here. And what you're looking for is the first positive result. And there we go. There's one right there. Buckling mode 35. It says it's going to fail at 106.3 times the load. Well, the load we put on there was 1 Newton. So at 106 newtons, or about 10 kilos, it's predicting this structure is going to fail in this mode. Now, what does this design show right here? Well, actually, it shows a lot like what we predicted before. As you rotate around right in here, you can see that we've got a buckling failure. This is being pulled down right here. Okay, as that gets pulled down here, it puts this member into tension and this member into tension. They're being pulled down that way. You can see that our buckling is going to be caused by this node popping out to the side. Now, will it pop that far out to the side? It's hard to say. There is a deformation thing right in here that allows you to adjust the scale of the deformation. We're not rubbery enough to have it pop that far out to the side. It might pop that far out to the side before it fails. It's kind of hard to say. Doesn't really matter. Once it's buckled, it's failed, it's popped out to that side, and we can tell that we're looking at a buckling failure in the back right here, which is nice because as you'll recall, a little earlier, we sat down and did some math on our sheet of paper, and we said, hey, look at this. We've got our longest members subject to our highest load back there. I'll bet that's where the buckling failure is going to be. We may probably need to make those nodes a little bit stronger. So that's confirmed right on there. But what this does is it gives us an idea at what force that's going to happen at 106 newtons. Now, is it going to be precisely 106 newtons? Well, we didn't quite have the perfect material in there, okay? But what it does tell us is that we need to make that part of the structure stronger. And you'll notice that out here, we have very little buckling happening out here. Now, how hard would we have to push to cause this side out here to buckle? Well, there's all these different failure modes. And if for some reason it didn't buckle at 106 newtons, keep coming down and looking for the next positive failure. Here we go, buckling mode on my design. It's at 148. If it didn't buckle right there at 106, we'd have to get up to 143 almost, and then what you'd see is a buckling failure right in here along this side, which kind of makes sense that that would be our next buckling failure. But we won't get there if that fails at 106 because we'll never be able to apply 143 newtons of force. As you go further into the structure, I asked for 80 calculations, and there's a negative response. Some of them are just silly. Like I say, garbage in, garbage out. If you were ever able to get up to 173, this is another buckling mode that could affect this member coming right down there. But again, anything past your first buckling node right here, mode at 106, is mostly for entertainment value, okay? Because this structure is going to pop out to this side due to a failure in the back right there. We need to do something about that before we go on. Now, there's one more thing that this can answer for us. Right now, this is only looking at buckling, and we have some members that are going to be loaded in tension as well. And down here in the bottom, okay, we've already said these aren't going to buckle because they're under tension, but are they going to hold together under tension? To do that, we need to do one more study. So let's say that this thing can hold 106 newtons, pushing down right there. Okay, now you know where it's failing. You know where you've got too much material. You know where you've got too little material. You can go back into AutoCAD and you can redesign that to either shorten these up by putting a couple of nodes in there. Remember that your nodes can't be any closer than 70 millimeters together, so you might be only able to have one node in there. Oh no, that's a 270 millimeter long stretch from there to there. So you could fit two nodes in there. Maybe you shorten those up and that really stiffens the back. Okay, maybe you pull one of the nodes out right from here and spread these apart a bit further, and that reduces the amount of material. Maybe you just come in here and you widen these pieces a little bit to make them stiffer and more resistant to buckling. Maybe you narrow these ones to make them less resistant to buckling so that you're putting your material where it needs to be and you're using your 75 grams as effectively as possible. Alrighty, let's take a look in here at what happens if we look at the linear static stress analysis. Okay, so we want to know, do these members hold together when we put 106 newtons right down in there? To do that, we need to have a new a new study. So what we're going to do is we're going to come in here and, oh, we got to finish our results. Click on the little green arrow. And right up here under study, we're going to create a new simulation study. And this one's going to be a linear static stress. Go ahead and create a static stress study and flip it up so it's in the right plane. Yeah, I know I made that look pretty easy with the mouse. And then go ahead and we're going to put the same constraints on it. Okay, so our structural constraints, we're going to have a pin that's free in the tangential direction to rotate right down there. We are going to have a structural constraint that is going to be free to slide forwards and backwards this way. That's the X direction, so I free up the X direction and apply it right there, but it can't go up and down or side to side. And then I am going to apply a load right on here, a structural load right at the middle right in here, and I'm going to use the vector mode so it knows that it's always pointing down, and I'm going to have it point down with a direction of 1 Newton, or sorry, 106. We used the 1 Newton to find out where we were going to buckle, and it said we'll buckle at 106 times 1 Newton. So now I want to say, well, if it's going to buckle at 106, will it break before it gets to 106? So I put 106 newtons right in there. Now, because this is your first time using Simulation and Fusion 360, I have simplified a few of the things that we're doing right in here. I've skipped over getting the absolute perfect material coordinates in there. And as you can see when we do our testing, our loading jig is slightly different from always providing a perfectly downwards vertical force distributed evenly across this member. It's close enough that these results are going to be meaningful to guide your design, but if we're off by a couple of numbers, that's okay. Alrighty, let's come in here now. We've applied our constraints, we've applied our load, we have a structure that's got a material assigned to it. Now we can come into our solve and we can tell it to do a solve. If you've got a moderately speedy computer, this one can be done locally and you can solve it on your own CPU and save Autodesk the hassle of having a whole bunch of students solving introductory problems on their servers. If you're running on a Chromebook or something like this and it's just bogging down running Fusion 360, go ahead and solve it on the cloud. That's why it's nice to have access to Autodesk's CPUs. So I'm going to solve this one locally and press go. And there we go. Now my CPU will gear up. So I'll just stop recording for a second here and we'll take a look at the results when it's done. Well, that was definitely speedy. And oh, a little warning for me. I'm just gonna close this message right here. And this is kind of nice. I'm only getting the orange sign. Okay, the orange, got to read your message right in here. The design is marginal. It may be sufficient, but outside factors for design applications. A minimum safety factor of 3 is common. This is not a typical design application. Here you're building something with the intent of breaking it. You want to make it as strong as possible. And what this is telling us is that you could probably support that 106 newtons that it predicts for the buckling failure. There's times, like if it had predicted that you were going to be able to support 150 newtons in buckling, you might have got a warning in here saying that your safety factor was less than 1, which is almost a guaranteed tensile failure before reaching your buckling force. Okay, so I'm just going to close this warning for a second and take a look at what the pretty picture results tell us right here. Okay, now it's deformed the structure, and since we're doing a 2D analysis, you can kind of look at it from the side and the results should make sense. Now, this is massively exaggerated in how much they've moved. So we've put a force down here, so this node has moved downwards. That makes sense. Things have kind of stretched in right here. Again, our deformation has been magnified quite a bit. If you come in here and say, what would the actual deformation be? Okay, this is what your actual deformation is going to be. We're talking millimeters. It's not that exciting. But what is useful right in here is that it's telling us what our safety factor is going to be. Okay, and the safety factor is how many times stronger it is than it needs to be in order to support that 106 Newton load we put on it. And so anything that's yellow is really getting close to that safety factor. So when I look right in here, okay, these members where we have buckling are also getting very close to failure under under tensile or compressive loads. Okay, that just they're reaching their material limits, and that's probably part of why we saw the buckling back here. But if we come out and we look at the green and the blue stuff, okay, this stuff is nowhere near its limits. It's 7 to 8 times stronger than it needs to be. Now, if you want to know exactly how many times stronger, you can come in here and you can go inspect and tell me create a point probe, and you can come in here and you can click there. This member is like 13, 14, 15 times stronger than it needs to be. So there does need to be something right in there, but maybe I can massively reduce that size, reducing the weight of that member, allowing some more weight to come over onto this side right here. Right up here, now I'm at 4, 5 times. That's a really long member right in there. So under linear static stress, it's not having that big of a problem. As we saw in our buckling, because this is going to be supporting a compressive load, we can't go too much lighter out here. So you have to take these two different failure modes into account while you're thinking about what's going on in here. But down along the bottom right here, this member is all like 1.5. We get up to 2 in there kind of. You know, maybe I just needed to make that bottom just that hair thicker so that it's a little bit safer. It doesn't add that much to the mass, but would would definitely ensure that I'm less likely to have a structural failure due to a tensile failure in the bottom right here. Okay, so based on what I've seen in my Fusion 360 drawings, I've probably got too much meat coming down right in here in these blue members and not a lot of force coming up here into these blue members. I can lighten them up. Okay, to resist buckling, I can switch over to my buckling study right here. Click on the little dot to get back to it and then tell it that I want to take a look at the results. Okay, I can also see that I wasn't really suffering too much from buckling in there, but right back here at the very back, as I predicted by hand, you can see that I've got a failure coming in right here. And if my hand predictions and my understanding of the structure jibe with what the computer is telling me, then that probably means that I can reduce some of the material out here, shift it back over to here, and use my 75 grams to create a stronger structure. I can also take a look at that and say, well, is this stuff up here doing very much for me at all? And I might be able to lop that top off entirely, or change this up so maybe this comes down in here, or all sorts of different designs and iterations that you can do on your computer. But these are iterations that you can do at home. And then when you come in for your lab on Thursday, you'll have a structure that's been through a couple of computer design iterations that you'll be able to test and see how carefully your prediction matches what Fusion 360 predicted. Now, this is my video on one workflow for creating this structure. And I chose to use the AutoCAD Dxf imported into Fusion 360 workflow because I know the students at BCIT are learning AutoCAD right now, and this is actually a great way to get in and do your offsets, do your trims, do your fillets, and just churn out a cool, useful tool from AutoCAD. If you're really interested in Fusion 360, I have another video up on my channel that talks about doing a parametric design for a truss so that when I say add a bit of material right in here, you can just come back and change some of the numbers. It doesn't allow you as much flexibility in where you put the nodes, or in how many nodes that you have. You kind of have to commit to the number of nodes at the beginning, but you get a bit more chance to play with the location and a bit more chance to rapidly edit the width of some of the members on there. It was designed for a different loading scenario. So you have to take the information on this loading scenario, and when you set up your study in that loading scenario, you have to sort of understand what's going on there. But the cool thing is, if you can do that, then you probably have a good understanding of what you're doing, and you can probably make it work in either way. So there is a video up there. Let me just pop over to YouTube and let's see, your videos are your channel and somewhere in here. Let's see if I can find the title so that if you're looking for it, it's got a nice picture of a bright, lovely Fusion 360 drawing on the cover right in there. There we go. And so oh, no, that's not it. That's an entirely different use of bright Fusion 360 colors. There we go. Using Fusion 360 to simulate a truss. This goes in and it shows you how to do a parametric setup so that you can then edit parts of the truss fairly easily in Fusion 360. So you've got a few different options to simulate your truss, but given that we don't have as much time on the laser this year as we have in previous years, good computer simulation is going to be very helpful to getting a competitive truss design. Thank you very much, and good luck with your modeling and simulation. I'm looking forward to seeing some laser cut trusses in the shop.